I'm tackling a problem involving Gaussian process regression, a powerful machine learning technique used for regression tasks. The core of GPR lies in its kernel, which dictates how the model learns relationships in the data. I'll be focusing on optimizing the kernel to improve model performance. GPR uses kernels to model the relationships between data points, and this optimization will be crucial. The original model uses a combination of kernels, RBF, radial basis function, which models smooth patterns in data, and white kernel, which accounts for random noise. The 1.0 scales the RBF kernel's influence. Length_scale equals 1.0 controls the smoothness of the RBF. A smaller value makes it less smooth, and noise_level equals 0.1 sets the magnitude of the noise. I'm looking at improving this combination to better capture both smooth trends and noise. I'm trying to improve the Gaussian process regression model's accuracy by carefully adjusting its compound kernel. A compound kernel allows me to combine different kernel types for a more nuanced representation of the data. This question tests my understanding of how kernel choices and their parameters affect GPR model performance. I'm considering replacing the RBF kernel with a less smooth version by reducing its length_scale from 1.0 to 0.1. This change will make the model more sensitive to local variations in the data, potentially capturing details that the smoother kernel missed. Think of it like changing a wide brush for a more detailed brush stroke. I'm exploring lowering the noise level in the white kernel from 0.1 to 0.01. This is a way to reduce the amount of assumed noise, which can improve accuracy if I had overestimated the noise. By adjusting noise levels, I am finding a good balance between overfitting and underfitting. I'm thinking of adding a rational quadratic kernel to increase the model's flexibility. The rational quadratic kernel provides a broader range of smoothness compared to the RBF kernel. I am effectively adding more adaptability to the model. I'm considering removing the white kernel entirely. However, this would assume no noise in the data, which is highly unlikely. Removing it completely might lead to overfitting. My model would fit the training data too closely and not generalize well to new data. I'm looking for kernel modifications that improve a Gaussian process regression (GPR) model. Specifically, I want changes that help the model better represent both the smooth patterns and the random noise in the data. Think of it like fitting a curve to points that have some random scatter. I need to find the best way to capture both the underlying curve and the noisy deviations from that curve. This is important because a good model needs to fit the overall trend while acknowledging the inherent uncertainty or noise in the data. The radial basis function, RBF, kernel models smoothness. A smaller length scale means the RBF kernel becomes less smooth, making it more sensitive to local variations in the data. Think of it like using a shorter ruler to measure. You get more detail but might lose the overall picture. I'm changing how smooth the RBF kernel is. A smaller length scale makes the model more flexible and able to capture details. So, I'm potentially making it better at fitting the data closely. The white kernel models noise in the data. The noise level parameter controls how much noise the model expects. Reducing the noise level makes the model less tolerant of noise. I'm adjusting how much noise the white kernel accounts for. By lowering the noise level, I'm telling the model that there's less random fluctuation in the data than it initially thought. This could lead to a better fit if the initial estimate of noise was too high. The rational quadratic, RQ, kernel is another smooth kernel, like the RBF, but offers more flexibility in representing different levels of smoothness. I'm adding another type of smooth kernel. This increases the model's ability to fit different types of smooth curves, making it more versatile in fitting the data. The model becomes more adaptable to complex data patterns. The white kernel represents the noise in the data. Removing it assumes there is no noise, which is usually unrealistic. I'm considering completely ignoring any noise in the data. This is almost always a bad idea, because real-world data is rarely perfectly smooth. Ignoring the noise will likely lead to overfitting. The model will fit the noise too closely, making it perform poorly with new data. These are the options that are likely to improve the model. Options A and B refine the existing kernels by adjusting parameters. Option C adds another kernel to improve the overall flexibility in models fitting. I'm concluding that the best modifications are A, B, and C. They address the issue by improving the model's flexibility and better accounting for noise. I'm using Gaussian process regression, a powerful machine learning technique. It uses kernels to model the relationships in your data. Think of a kernel as a function describing how similar data points are. Optimizing the kernel is key to a good model. GPR uses probability to make predictions, making it more robust than some other methods. I want to improve a Gaussian process regressor model. The model uses a CompoundKernel, which is a combination of simpler kernels. My goal is to find the best combination to capture both smooth trends and noisy variations in my data. Think of it like trying to fit a curve to some data that has a smooth underlying pattern but also some random noise. My current model uses a kernel that's a sum of two parts. The RBF, radial basis function, kernel captures the smooth trends, and the white kernel accounts for the noise. The numbers length underscore scale equals 1.0 and noise underscore level equals 0.1 are parameters that I need to tune. A larger length scale in the RBF means smoother trends. A larger noise level in the white kernel means I'm assuming more noise in the data. I'm considering replacing the RBF kernel. I'll make the new RBF kernel less smooth by reducing the length scale from 1.0 to 0.1. This could help capture smaller details and sharper changes in the data that a smooth kernel might miss. I'm exploring changing the white kernel. By reducing the noise level, I'm assuming less noise in the data. This could be useful if the original noise level was too high, making the model too smooth and unable to fit the data accurately. I'm thinking of adding a rational quadratic kernel. This is another kernel that captures smooth trends. But it's even more flexible than the RBF, so it might do a better job at modeling various degrees of smoothness in the data. This offers more flexibility than RBF alone. I could remove the white kernel, but this assumes no noise in the data, a risky simplification, especially for real-world problems. This would likely lead to overfitting, so it's not a good idea. I'm changing the radial basis function, RBF, kernel's length scale. A smaller length scale, 0.1 instead of 1.0, makes the model more sensitive to local changes in the data. Think of it like this: a larger length scale smooths out details, while a smaller one lets you see the bumps and wiggles. This could be great if your initial model missed some important fine-grained features. Here, I'm tweaking the white kernel, which models noise. A smaller noise level, 0.01 instead of 0.1, tells the model that there's less random noise than initially assumed. This is helpful if your previous model was too cautious about overfitting and oversmoothed the data. It helps the model fit the true underlying pattern better. I'm adding a rational quadratic kernel to my CompoundKernel. This gives the model more flexibility to handle various levels of smoothness in the data. The RBF kernel assumes a specific type of smoothness, but the rational quadratic kernel lets you represent different kinds of smoothness. Think of it as having more tools in your toolbox. You can fit the data much better. I would remove the white kernel. This is generally not a good idea. It's highly unlikely that real-world data has no noise. This simplification would probably lead to a poor model that doesn't reflect reality. The model would likely overfit and not generalize to new data. I'm trying to improve a Gaussian process regression, GPR, model by tweaking its kernel. A kernel defines how the model measures similarity between data points. Think of it like this: a kernel is a recipe for how your model learns from the data. I want to find the best kernel recipe to make the most accurate predictions. My starting point is a kernel that combines two parts: RBF, radial basis function, and white kernel. RBF handles smooth patterns in the data, while white kernel adds noise. The equation 1.0 asterisk RBF, length underscore scale equals 1.0, plus white kernel, noise underscore level equals 0.1, means the RBF part is multiplied by 1 and the white kernel has a noise level of 0.1. I'm trying to adjust these to improve model accuracy. This option changes the RBF kernel's length scale parameter from 1.0 to 0.1. A smaller length scale makes the RBF kernel focus more on local details. Think of it like zooming in on a map. It can help if the model initially missed capturing small, quick variations in the data. Here, I'm adjusting the white kernel's noise level from 0.1 to 0.01. This reduces the amount of noise the model expects to see. If the model was initially assuming too much noise, this change makes it more focused on actual patterns instead of getting distracted by random fluctuations. This adds a new kernel type called rational quadratic. It's like adding another tool to my modeling toolbox. This kernel, similar to RBF, models smooth trends but offers more flexibility in how smooth it is. Think of it as a more versatile smoother that lets me fine-tune the smoothness level for a better fit. This option completely removes the noise component from the model. That's a big no-no. Real-world data almost always contains noise, and ignoring it usually makes the model overfit to the training data, performing badly on new data. This describes the effect of changing the RBF kernel's length scale. A smaller length scale, like in option A, results in a less smooth model that can better capture local, smaller scale variations in the data. This explains the impact of reducing the noise level in the white kernel, option B. If the model initially assumed too much noise, reducing this level prevents overregularization, which can make the model too smooth and miss important details. This is the benefit of adding a rational quadratic kernel, option C. It enhances the model's ability to capture complex data patterns that might not be fully represented using just an RBF kernel. Removing the white kernel, option D, is risky. It assumes the data has no noise. Ignoring the inherent noise in data causes overfitting, resulting in a model that performs well only on the training data and badly on new unseen data. I'm focusing on the building blocks of the kernel, the individual kernel functions, because understanding them is key to combining them effectively. A kernel is like a recipe. Each ingredient, kernel function, contributes specific properties. The radial basis function, RBF, kernel is my go-to for modeling smooth, continuous functions. Think of it as capturing the overall trend in your data. The _length underscore scale parameter controls how far the influence of each data point extends. A smaller _length underscore scale means more local detail. A larger one means a smoother, more global picture. The white kernel is all about noise. It models independent, random fluctuations in the data that aren't explained by the smoother parts of the model. The _noise underscore level parameter controls how much noise you expect. A larger value means more noise. The rational quadratic kernel is more flexible than RBF. It allows for varied smoothness, seamlessly blending local and global effects. It's like a supercharged RBF, giving you more control over the shape of the trend. This is where the magic happens. A compound kernel lets you combine multiple kernels, like RBF and white kernel, to capture both smooth trends and noisy fluctuations in your data simultaneously. It's my way of getting the best of both worlds. I'm using Gaussian process regression, a powerful machine learning technique, to model data. A key part of GPR is the kernel, which determines how similar data points are. I'm optimizing the kernel to improve the model's accuracy. I'm trying to build a better GPR model. My current model uses a combination of kernels, CompoundKernel, but it's not performing as well as I want. I'm figuring out how to change the kernel to get a better fit. My starting point is a kernel that's the sum of two parts. The radial basis function, RBF, kernel models smooth trends, and its length scale, 1.0, controls how quickly the trends change. The white kernel models random noise, with noise level of 0.1. I'm considering changing the RBF kernel's length scale from 1.0 to 0.1. A smaller length scale means the model will be more sensitive to local changes in the data, potentially capturing finer details. I can also adjust the white kernel's noise level from 0.1 to 0.01. A lower noise level assumes less randomness in the data, potentially leading to a better model if the original noise level was too high. I'm exploring adding a rational quadratic kernel. This kernel is similar to the RBF but offers more flexibility in capturing different levels of smoothness. I could remove the white kernel entirely, but this assumes the data has no noise at all, which is unlikely in real-world scenarios. This would probably lead to a poor model. These are the various ways I can change my kernel to improve my GPR model.